Hello, my name is Cayman. I decided on an implementation project related to recurrent neural networks that can learn binary arithmetic. So, I decided to perform binary addition with my neural network on 4, 8, and 16-bit integers. This training data was generated with a Python script that I've included in my project submission. So what does the network need to learn? The carry bit. So suppose we want to add the following two 4-bit binary integers. Notice the carry bit moving from right to left. This is what the RNN is going to learn. So as you see here, moving from right to left. As we perform our addition, we need to carry this 1, and that's the carry bit that the network's going to learn over time. So here's the basic architecture of my recurrent neural network, where you have your U, that's your input matrix connected to the hidden layers, W, which is your hidden to hiddens, and V, which is your output layer, which is connected from your hidden to your output. So one quick thing too, notice the unfolding at each step. Those are the time steps, and those time steps for my recurrent network are related to the size of the binary integer we're learning from, so whether it be 4, 8, or 16 time steps. So forward propagation. First we're going to randomly initialize the matrices like we've done before, the U, W, and V. I'm just using the rand_n function in Octave for those. The dimensions of the weight matrices are as follows. You can see here we have 2 inputs and 1 output. For the input matrix, with the 2 inputs, basically if you move from right to left here over time, so the X would be these 2 digits here, and the target value would be Y. For this would be 1. And then these 2 digits, target value 1, these 2 digits, target value 0. So you get the idea. So a forward prop through time for the RNN, basically all these calculations here you see are calculated per time step. So whether it be 4, 8, or 16, like I described before. So the current hidden layer to be used at the next time step is what we're calculating here. And if you notice this hidden layers cell, that's used to basically keep the previous hidden layers at the different time steps. So at the end of each time step iteration, you'll set this cell equal to this calculated hidden layer to be used on the next iteration, as you see here. The rest of the forward propagation is similar to our first feed-forward networks we created, where you have basically calculate the output activations, derivatives that we backpropagate, training cost. The predicted binary vector, that gets updated per time step as well with the correct digit place based on the output activations, and we're rounding like we've done before to get a 0 or 1. Backprop through time, these are also all done or calculated with each time step. One thing to notice here is we're applying t+1 hidden deltas at this time step to the hidden weight matrix transposed. So basically this hidden deltas at the end of each time step gets set to this hidden delta that was just calculated. We also need to accumulate the weight updates for each matrix before applying the changes to U, W, and V. So that's what you see here. These matrices here are updated within each of the time steps. So when you're done with all the time steps, you can update the actual view W and V matrices as we see here with the updates and the learning rate element-wise. Also, we'll need to, before running another training example, we have to zero out these update matrices. So here are some of the predictions from my RNN. As you can see, 6 plus 2 is 8, and it predicted 8. 5 plus 4 is 9, predicted 9. And here's some of the results: training, testing, validation for different epochs. I'd like to improve this in the future. As you can see, it is learning, but accuracy in the early epochs is not spectacular. So hopefully by adjusting some of the hyperparameters and size of the training data and those sorts of things, I can improve some of these numbers in the future. Well, that concludes my presentation on recurrent neural networks capable of learning binary arithmetic. Thank you.